Super. Good morning, good afternoon, everyone, and welcome to today's IR webinar in partnership with the European Sustainable Energy Week, called Cooling Without Further Warming Our Planet. Today we will speak technologies, energy efficient air conditioning, and heat pumps. My name is Suhir Hamemi, and I will be your moderator today. On behalf of the IIR, International Institute of Refrigeration, it's a real pleasure to have you and to be with us. We are gathering today in a very important moment as Europe accelerates its push toward climate neutral economy under the European Green Deal and REPowerEU. Cooling and refrigeration is becoming important and responsible as it is responsible for a significant share of the global energy use and greenhouse gas emissions. It is finally taken center stage in the energy policy conversations. Over the next hour, we will hear from two leading experts, explore the latest technology advances, discuss policy, and open the floor to your questions. A quick housekeeping note, there is a Q&A button that you can use for the questions. We will address them at the end of the session after the two presentations from the two professors, Björn Palm and Yunting Ji. The webinar is being recorded and it will be made available for all registered participants on IR network on our social media and YouTube channel starting from tomorrow morning. I'm honored to be together today with Professor Yunting Ji and Professor Palm. First, I will start with Professor Björn Palm. He will be responsible of the first speaking slot. Professor Palm is a leading expert on heat pump technology. He's a member of IIR Publication Subcommittee, member of IIR Management Committee, and delegate of Sweden to IIR. Thank you, Professor Palm, for being part of the support and mentorship to all IIR scientific and information products and being part of this webinar. Professor Palm is based in KTH Royal Institute of Technology in Stockholm, where his research has fundamentally advanced on understanding two-phase flow and compact heat exchangers. Beyond the labs, he has been instrumental in shaping international scientific standards and policy recommendations in the heat pump sector, bringing rigorous science directly into the rooms where decisions are made. Very happy to have you today, Björn Palm. The floor is yours.
Thank you, Suhir, for the very nice introduction. So the topic of the speak today, let's see if I can change slides here. Now it comes. I call it heat pumps and as high efficiency heating and cooling systems. So even if the main focus on this week is on cooling, I think it is important also to mention heat pumps, as heat pump equipment can be used also for cooling. And perhaps the heat pumping itself is more important than the cooling, as we'll see shortly. So let me start by showing an overview. So first I'll start with an introduction and something about use of energy for heating and cooling, effects on the environment, development plans, and finally some words about the implementation of new research findings and a conclusion, of course. So as an introduction, we cannot, I think it's important to show this slide again and again. We know that the temperature of the world is rising, and this is a threat to the society, the stability of the society as we know it. And for this reason, we have agreed, most countries of the world, to phase out or to be carbon neutral in about 25 years from now. And 25 years is not that long time. So we have to really speed up the process of reaching there. And one activity which is ongoing right now is a conference in Colombia on transitioning away from fossil fuels. So this is an international collaboration with more than 50 countries. And I think this is a good sign that we are actually working towards the transitioning away from fossil fuels. I have some problems switching. Okay, now it works. So let me start by giving you some statistics and talking about the use of energy for heating and cooling. And actually, about heating and cooling counts for about half of the global final energy consumption and is responsible for more than 40% of the global energy-related CO2 emissions. So it's not a small share; it's a very large share of the total energy use which is used for heating and cooling. We should remember that. So that's why this is important. Let's look at some more statistics here. This is showing the energy mix in the EU. And as you can see, about 69% of all energy used in the EU came from fossil fuels in 2024. And then we have renewables 20% and nuclear 12%. If we continue looking at how much fossil fuels we were using. So about 66% of all heating in the EU was by fossil fuels in 2020. That's the last statistics I saw. And actually, at that year, heat pumps only contributed to about 1% of the heating. The rest, then we have renewable biomass and renewable, which covered about 30%. Continuing with some of the statistics, if we look at the households in Europe, the heating stands for about 77% of the energy consumption in the households, while cooling stands for less than 1%. So if we're just looking at the households, cooling has a much, much smaller effect on the global warming than the heating does. And of course, you may argue, if we go to heat pumps, where does the electricity come from for these electrically based heat pumps? Actually, in 2024, more than 47% of the electricity in the EU came from renewables, and more than 23% came from nuclear. So this means that in total, about 70% of the electricity were non-fossil. So a relatively large share of the electricity is produced by other sources than fossil fuels. So where are we and where do we need to be? Well, obviously, if we need to electrify the heating sector as well. And this is from a publication by Arena. In their 1.5 degree scenario, you can see that the number of heat pumps need to be increased considerably, both in buildings and in industry. So going from about 58 million heat pumps 2020 to some close to 450 heat pumps in 2030 and close to 800 million heat pumps in 2050 for buildings. And similar development need to be in place for the industry, going from less than 1 million to about 80 million heat pumps in 2050. Similar projections are made by the IEA. And the IEA says that installation of about 600 million heat pumps, covering about 20% of building heating needs, is required by 2030 if we want to be on track towards carbon neutrality. So there is a lot to do. Unfortunately, we are not moving as fast as we should, and the number of heat pumps installed is not by far as high as it should be if we want to keep to this track. Sorry about that. Now, looking at the statistics for Europe, we can see that the sales of heat pumps increased exponentially up until 2022. Then we have had a dip for 2 or 3 years, but now the latest year, 2025, the sales has increased again. So we are increasing the sales of heat pumps, but it's not going quite as quickly as we would like to. Now, looking at the EU policies, we have, of course, several activities to reduce the emissions of carbon dioxide. One is Fit for 55, where the target is to reduce emissions by at least 55% by 2030. Another activity or action is REPower Europe, where the goal is to reduce the dependence on Russian gas mainly. And then we have the Net Zero Industry Act, which is supporting net zero technologies, where heat pumps is considered to be one of the technologies then. And in total, it's estimated that we have about 60 to 65 million gas heaters in Europe, which need to be replaced within the next 25 years or so. And according to the decisions in the EU, we have a goal to install at least 10 million heat pumps from 2023 to 2027. Unfortunately, I think we will not be able to reach that goal. So let's talk a little bit about the effects on the environment from the use of cooling and heating. The environmental impact can be reduced in several ways. One way is to increase the efficiency of air conditioning equipment and heat pump systems, of course, equally important in both cases. We can also substitute gas and oil heaters for heat pumps. And of course, this is very much more important than increasing the efficiency of the air conditioning and heat pump systems. Because substituting the gas heaters or oil heaters having an efficiency of less than one for a heat pump with an efficiency of 300% or 400% or even more, that will be a great gain. We can also reduce environmental impact by use of refrigerants, which first give a high efficiency and second are environmentally benign. So let's look a little bit more on this. I'm sorry for the slow switching here. The system is not quite working as I would like to. Yeah. So last year, or 2024, we had a new F-gas regulation. And there are two parts to this. One is the phase out of HFCs. And as you can see, by 2050 from this graph, the plan is to have stopped using HFCs totally. However, this does not include the HFO refrigerants. The other part of the F-gas regulation is the ban to sales of certain products. And in this table, you can see to the left, monoblock heat pumps and air conditioning equipment, and to the right, split heat pumps and air conditioning equipment. And for each year, the regulations gets more tense. So by 2032, it will not be allowed to sell monoblock systems with a capacity less than 12 kilowatts with any type of F-gases. And from 2035, there is a ban of split systems with capacities less than 12 kilowatts with F-gases. So this means that in less than 10 years from now, we will only have the natural refrigerants as fluids in our small systems. In large systems, there will still be allowed the synthetic fluids. There is also a proposal to ban any type of PFAS substances in Europe. And we should realize that almost all HFCs and HFO refrigerants are PFAS, according to the OECD definition. And we should also realize that F-gases constitute about 38% of PFAS emissions worldwide. So it's not a small share of the PFAS. And even though the HFO refrigerants cannot be called forever chemicals as they fall apart rather quickly in the ambient, still some of them at least form trifluoroacetic acid as they decompose, TFA. And this is a substance which is increasing in concentration in the ambient, especially during the last 10 years. And already the concentrations in the drinking water in several cities in Europe are above the recommended levels. So what has this led to? It has led to that most of the major European heat pump and air conditioning manufacturers are developing products for natural fluids, and mainly for propane if we talk about smaller systems. There are also many Asian producers which offer propane products for the European market. There are a couple of manufacturers in US producing propane systems, mainly for larger systems, not for consumer products. And of course, components in the US are also available in Europe. So let's have a look at development trends. Of course, I already mentioned that we are forced to go towards natural refrigerants. And this diagram shows the development from 2017 to 2024. In 2017, 410A was the most common refrigerant in the models of heat pumps sold in Europe, while in 2024, R32 was the most common, but R290 was responsible for 38% of the heat pump models. So this is not the sales. It is based on the HP Keymark database, where all of the products voluntarily can be added if they fulfill the requirements to be sold in Europe. This is some other statistics showing the sales of heat pumps in the EU from 2011 to 2023. And we can see that expressed as a percentage, the air-to-air heat pumps have been decreasing, while the air-to-water has increased, and the water-to-brine heat pumps have decreased also. But we should remember then that during these years, the sales have increased by a factor of 3 or 4. So this means that even the air-to-air heat pumps have actually increased a bit during these years. But the most of the increase is in the air-to-water heat pumps. So that is one of the trends we see. Let's look at some of the products here. This is an example of a product on the market with propane as refrigerant. It has a capacity of up to 6 kilowatt, can be used for heating and cooling. It's a water-water system, and as the charge is low, 150 grams, it requires no ventilated enclosure or no propane sensor. It consists basically of 2-plate heat exchangers. It doesn't have an internal heat exchanger or desuperheater, and the COP of this type of system is 4.3 under these conditions. So this is an example of a type of product which is coming out on the market now. For larger systems with propane, we need to have some more safety designs. So this is an example of a system which is available in 2 sizes, from 2 to 10 and 4 to 16 kilowatts. It has a tight ventilated enclosure with a constant underpressure. Sensor stops the compressor in case of a leak, and there is also forced ventilation to the ambient in case of a leak. So this is another type of product than for slightly larger capacities compared to the smallest ones with more than 150 grams of propane. I will show you one more example here. This is a heat pump with a capacity of 6 kilowatts, and all the refrigerant containing parts are built into one small box at the bottom of the heat pump. And basically you could have 2 such boxes within the heat pump enclosure. In that way you would get a capacity of 12 kilowatts. And the idea here is that rather than doing servicing on the spot, you just bring this box back to the company or to the service center to fix it if there is something wrong. So this is, I think, is a type of product which we may see more of in the future. This small box can also be used for small apartment heat pumps, of course. But heat pumps are also being used in larger systems. We see them more and more in district heating systems. This is an example of a 50 megawatt heat pump, which is now being installed in southern Sweden. The heat source is a wastewater heat treatment plant, and the refrigerant in this case is isobutane. So we see several hydrocarbon heat pumps, but also even more perhaps carbon dioxide heat pumps in district heating being installed right now. So that's another trend if we talk about the development. Looking at the statistics for district heating, I just want to point out that we will need quite a lot of heat pumps in the future. This comes from something called the Heat Roadmap Europe. And if you look at the development here from 2023 to 2030, you can notice that the light green at the bottom, which is representing the large-scale heat pumps, it's very, very small in 2023. And the dark green is the combined heat and power plant. And as we move towards 2050, the heat pumps have a much larger share. But looking higher up in the column here, we can see that heat pumps will also be used for recovering heat from waste heat sources of low temperature. So actually, if you look at how large share of the systems will be using a heat pump in one way or another, it's much more than this lower light green part which you see here. A couple of words on the research. A lot of it is focusing on decreasing the system charge in order to maintain safety with the flammable refrigerants. And this was from Sweden. This is another example from Germany in the LC150 project, where they're looking at different combinations of components to make the best possible heat pump with 150 grams of propane. And in both of these projects, we have shown that it's possible to get use about 10 grams of refrigerant, hydrocarbon, per kilowatt, much, much less than it's presently used in commercial systems. Yeah. So finally, coming to the implementing the charge, I will just say a few words about this in the interest of time here. Of course, the heat pumps and their AC equipment in the future, it needs to be affordable. We should go from gas heaters, which are relatively inexpensive, to heat pumps, which undoubtedly will be more expensive. But we need to look at the price and make sure that the cost is low. They need to be efficient, of course. They should be safe. They should have low environmental impact. They should be invisible. What I mean by that is that we cannot expect to have the walls of the buildings covered by outside units or condensers for the heat pumps or condenser evaporators for the heat pumps. They should have low noise because we will have many more of them. And of course, preferably they should be able to combine both space heating, domestic hot water production, and cooling. So my conclusions are the following. Cooling and heating requires about 50% of world's energy use. Global warming will lead to increased use of air conditioning, but global warming will also lead to or necessitate the phase out of fossil fuels and electrification of the heat energy system. And this electrification will lead to increased use of heat pumps, substituting gas heaters, reducing energy demand considerably. Heat pumps and air conditioning can often be combined in one unit, so it's not an opposition here. Synthetic refrigerants will be substituted at least in Europe for natural fluids, probably worldwide, but a little bit later, and mainly substituted for hydrocarbons. And there is a need for new products substituting gas heaters and air conditioners. Products which have a low cost and small footprint, which fit into an apartment which is now furnished with a gas heater. And looking at the industry, I think the European heat pump and air conditioning industry is strong, but it faces a tough competition, particularly from Asian countries. So that concludes my presentation. Thank you very much for your attention.
Thank you very much, Professor Pal. That was a very compelling and interesting presentation. I couldn't add more on your conclusions. Very complete. And one of the objectives of this webinar was also to make the highlight that heat pumps have that dual role of not as its name says just to heat, but it also cools for the different ranges of temperature that you presented. Now we move to our second presentation, and I think you will find out this builds naturally on your presentation, Professor Palm, but on a different scale of technology, district cooling. Our next speaker brings over 25 years of expertise spanning the built environment, refrigeration, energy conservation, hydrogen, and thermofluids. Professor Yunting Ji is a professor of building services engineering, president of IIR Commission E1 on air conditioning, and director of the Center of Civil and Building Services Engineering at London South Bank Universities. As a principal investigator, he has secured over £4.5 million in research funding. That's very interesting, Professor Newton-G. I think we should start fundraising together. And has published more than 140 peer-reviewed papers. He also serves as an associate editor for the Journal of Energy Reports. Very happy to have you, Professor Yunting-Ji, together today. Please, over to you for the next presentation.
Okay, thanks, Sophia, for your introduction. Hello, everyone. Thanks for attending my presentation. The title of my presentation is Energy Efficient Air Conditioning in Europe, particularly on district cooling systems. How to change to the next page? Okay. So the outline of my presentation are listed in this slide. It includes background, emerging trends in cooling demand, technological innovation, and what is district cooling principles, infrastructure, and key examples. Integration possibility. Integration possibility of different technologies for the district cooling, and understand the distributing pipe network and opportunities and the barriers and policy. And in the end, I will give some conclusion. So for the background, and as we know, buildings account for around 40% of total energy used in European Union, and of which I think about 65% is from residential buildings and 35% is from, service buildings. And buildings are also the major source of CO2 emissions, contributing significantly to climate change. So rising CO2 levels are raising global temperature and also intensifying global warming. Hotter summers and more frequent heat waves are expected to increase in cooling demand and also air conditioning usage in buildings. So greater use of air conditioning will increase electricity consumption and the pressure on energy systems. So a sustainable cooling pathway is therefore urgently required by improving building energy performance, reducing cooling demand, and developing more efficient cooling technologies. So for the cooling demand is directly affected by we call it the cooling degree days and also building profiles. The cooling degree day is determined by the climate, mainly the average temperature for ambient and also the population. And together, I think the cooling demand is directly affected by the cooling capacity of the energy supply system, So if we know the efficiency of the energy supply system, we will know the electricity consumption for the specific heat cooling demand. So we use equation 1, a simple equation, to calculate the cooling demand. Is a function of mainly the cooling degree days and the two coefficients, which are related to the building profiles. So if you want to calculate out the country's cooling demand degrees, country degree days. So if you know the regional cooling degree days and also the population, regional populations, you can utilize the equation 2 to calculate out the cooling degree days of a country. So for one of the cooling degree days, we all know about it. It can be simply calculated out of the temperature difference of the daily ambient average temperature and the temperature of the base of the building. So in Europe, I think the base temperature is specified as 18 degrees C. So under we all know the SEER calculation is the total cooling output over our season over the total electricity input over the same period. So from this calculation, what we know, if we have a lower ambient temperature, the cooling degree day will be reduced, and the actual cooling capacity will reduce, and correspondingly, I think the electricity consumption will be reduced as well. So if you have higher efficiency of the energy supply system, the electricity will also be decreased. So what we know here, so the ambient temperature will affect a lot for the energy consumption of the energy supply system for the cooling. So in this slide, it's showing about the ambient temperature profile in Europe. So in the left side, you can see the current temperature profile in Europe. What you can see here, the Northern Europe has a colder, I think, ambient temperature than the southern part. So I think that there are two, predictive models. We call it RCP 2.6. Another one is RCP 4.5 to predict the Europe ambient temperature in the next 10 and 30 years. So what you can see here, this is just to show you the temperature difference. You can see in the future, the ambient temperature in Europe will gradually increase. I think that the increase is about 0 to 2 degrees C. And what you can see here, the northern part can have a higher increase rate in the next 30 years. So what's the consequence of this? As we know from the previous slide, the higher ambient temperature will increase the higher cooling degree day, and then it could increase the cooling capacity and need more air conditioning usage in buildings. So the extensive utilization of traditional air conditioning, I think, can contribute more of the global warming. So here, I think, are some, static data, for the calculation of cooling degree days. You can see for the different countries. So you can see the decreasing of the cooling degree days depending on the location of European country. And the corresponding, you can see the yearly, I think, cooling, yearly specific cooling demand. So it's actually is decreased with the decrease of the cooling degree day. So in the right side of the diagram, you can see that in the next 5 years, the cooling specific cooling needed is increased about up to, I think, the 15%. And also the cooling degree days is also increased in the next 5 years. So what you can see from the left side of the diagram, so you can see roughly about the linear relation between the specific cooling demand and also the cooling degree day. Next page, please. Next page. Yeah. So this simple formula, I think we can roughly, verify. I think this formula to calculate out the cooling demand, I think is the linear relation between with the cooling degree day. So we try to reduce the cooling demand. I think there are two or three innovations which can be helpful to reduce the cooling demand. So one is to reduce the heat entering to the building so that it can reduce the cooling degree days impact. So what to do is to add more insulation and to have, I think, triple glazing, and also we add the settings for the building, which can reduce the U value of the external wall and then reduce the cooling demand of the building. So another innovation we can have is reduce the baseline and the internal loads by utilizing the ventilation, green roofs, and also smart controls. And the last one is to utilize in water AC instead of using the on-off control for the energy supply system. And also we can utilize the district cooling. So district cooling can not only reduce the cooling degree, they can also enhance the efficiency of the energy supply system. So in this presentation, I will concentrate on to introduce more the district cooling. So what is the district cooling? District cooling is basically a centralized air conditioning for a whole area instead of every building running its own AC. It leads into mainly three parts. So one is the central plant, and another one is the distribution network, and the last one is the building, the end user. So how it works, the central plant cools the water utilizing the chiller, mechanical chiller, and seawater lakes if they are available, or even ice storage for the thermal energy storage. And the cold water flows from the central plant. That one will flow through the closed loop underground distribution pipe network, with the temperature typically around the 4 to 7 degrees C. And at the building, that one takes this cooling from the central plant, where heat exchangers. And after the cooling, I think the warm water returns back to the central plant at temperature about 12 to 16 degrees C to be cooled again. So in this slide, you can see the performance comparison between the district cooling and the traditional air conditioning. So district cooling using central system instead of using the individual system. And the efficiency can be 2 times higher than the traditional system for the cooling, district cooling. But I think the capital cost is much higher than the traditional cooling because of the distributed network and also the central plant development and so on. And also the cost. The opening cost is about 20% and 40% lower than the traditional AC. And also for the CO2 emission is about 30 and 50% compared to the traditional AC. And this quite important part is urban heat island. I think the traditional AC can reach the 1 to 2 degrees local temperature increase. But the district cooling, because of the heat released in the remote site, it can reduce and also mitigate the urban heat island effect. And district cooling utilizes the supply temperature at 4 to 7 degrees C, and the return is at 12 to 16 degrees C. But the traditional AC just release the heat through the condensation process and locally. And here I'll give an example about the district cooling system that is located at Amsterdam in Holland. So you can see that on the right side, right top side, the photo, you have a number of buildings which are cooled by the district cooling system. Underneath, you can see the city layout, the map of the city, and you can see the city layout for district cooling. It includes the central plant, is the black block one. That one you can see a number of buildings, and also you can see the stick, I think blue lines, that is diffuse network. And connect to the central plant, you can see the lake, new I think mirror, which can supply the free cooling for the cold water. So the supply temperature is about 4 to 6 degrees C, and the return temperature is about 12 to 16 degrees C. So this lake can directly cool down the return water to 6 degrees C. So if the lake temperature is low enough, if the lake temperature is a bit higher, it will be pre-cool the return water before the chiller can be used to cool the cold water further. So I think the result, this district cooling system can reduce the CO2 emission by 75% compared to the conventional chiller system. So come back to the district heating. I think that it has the benefits which can integrate a number of the efficient system, including the renewable energy and the thermal storage system, and also a tri-generation, we call it CCHP system. For the renewable energy integration, renewables include wind, solar, biomass, and geothermal. For the thermal storage system integration, the thermal storage can be chilled water tank, auxiliary tank, and PCM tank. So for the CCHP system, it can utilize the fossil fuel to generate simultaneously the cooling, heating, and electricity, which can be used for district cooling system. So for the integration of renewable, I just utilize the solar as an example for as a renewable energy system integration. So the most important characteristic of solar cooling is that the peak solar production and the peak cooling demand often match quite well. And also solar cooling can implement it with both solar thermal and solar PV. Solar thermal, when it connects to the absorption system, the solar thermal can produce the cooling at the same time. So solar PV can generate the power, and the power can energize the chiller system to produce cooling. And it's not that the solar cooling can not only produce the cooling, it can produce the heating as well. Sometimes the heating is also required for the buildings. And this is the integration for the renewable energy for cooling. And for the tri-generation, we know tri-generation or CCHPs, it can simultaneously produce electricity, cooling, and heating. So if you have a CHP system, so if you can integrate it with absorption chiller, the CHP system can produce the cooling in the meantime. So if normally I think the fossil fuel gas is used for the CCHP system, so now so this system, the carbon dioxide produced by the tri-generation system and can also be captured and stored and utilized. So for the integration of a thermal energy storage system can store the cold energy during the period of a low cooling demand. If cooling demand is lower, you can store the cold access store energy to the storage energy, and in the meantime release the stored cold energy to meet cooling demand at different time than it was produced. So therefore, cooling storage positively impact electricity grids by reducing the peak electricity demand. In the meantime, I think that the cooling cost can also be lowered by shifting, I think, electricity consumption to off-peak hours where the energy prices are lower. So for the design, for the integration, it can see from this diagram, it can be the installation of a thermal energy system can be upstream or downstream or in parallel, something like that. So regarding to the second part of a district cooling system for the distribution pipe network, it can be used as the district cooling only. That one, it doesn't supply the heating in the meantime. So in that case, the district cooling only networks distribute chilled water purely for the space cooling and the process cooling. So that means some period in the year, so this network will not work if cooling is not demanded. So this district cooling only system are strong when the urban density is high and the cooling demand is large. And there are some limitations for this because it can't run, I think, the whole, operating time in the whole year. So limit the annual operating hours and the insufficient use of the waste heat. If waste heat is available, you can't transport the waste heat to the building, and difficult in balancing the cost and low carbon performance of the whole year. So another, I think, the underground between pipe work is combined district heating and cooling network. So one option is separate district cooling and heating network. You can see from the diagram, you have a four pipe system. Two pipes are used to transport the heating to the building from the central plant, and two pipes are used to supply the cooling from the central plant to the building. So the limitation is, although the district cooling and the heating technology are gradually matured, and the separate district cooling and heating networks still require two distribution systems, which leads to high investment and higher network complexity. And the last one is a newly development, I think, combined district heating and the cooling network is called the shared cooling and the heating networks. And we also call it the fifth generation district cooling and district heating and the cooling. So for this 5G DHC adopts a low temperature cooling and heating. It's using a two pipe system. You see this slide. And it's the temperature of supply is between 0 to 35. Is quite close to the ambient temperature and support yearly around, not like the district cooling only system. It can support the yearly around cooling and heating. So the heat pump, you need heat pump installed close to the building, the end user, so that the heat pump can extract the heat from the supply pipe, and also the actually reject the heat to the network, depending on the building is in the heating demand or the cooling demand. So the limitation of this, although the efficiency is quite high, I think the invested cost is quite high as well. And so we want the last one to talk about something about the opportunities, barriers, and the policy support for district cooling. So we have some opportunities. Consider about the high efficient low emission renewable integration and the lower peak demand. So there are a lot of opportunities for the application of the district cooling system, but there are some barriers. So one is the high capital cost, infrastructure capacity, and also the long payback. So we need some support from the policy, from the government in terms of incentives, climate policy, urban planning, and public-private partnerships. Finally, I give some conclusions. And building account for significant energy use and CO2 emissions in European Union. So raising CO2 levels are increasing ambient temperature and thus cooling demand. District cooling is one of the prospective technologies to reduce cooling demand and improve efficiency. District cooling system can apply free cooling and integrations of renewables, energy storage, and the CCHP system. The fifth generation district heating and cooling is a prospective district cooling system, but limited by the higher capital cost and operating complexity. There are opportunities, barriers, and necessary policy support for district cooling.
Thank you very much, Professor Yuntingji. Thank you for the very detailed and clear presentation. Now we move to the Q&A sessions. We received so many questions, and I hope we will be able to discuss and answer some of these. Let's start with the first question. Let me. Yeah, there is a lot of. Okay. Second question. So the first question, what are actual use of other natural refrigerants for high capacity heat pumps like R717 ammonia? Professor Palm, maybe that's question to you.
Yeah, I mean, there are several different refrigerants used for high temperature heat pumps, and they could be both hydrocarbons and ammonia, and also carbon dioxide to to certain temperature levels. So for these large systems, I would say that the refrigerant, how should I say, it's not such a clear case as for the consumer products where propane is totally dominating. There are several different refrigerants used, and ammonia is one of them, of course. Hope that is an answer to the question.
Thank you very much. Another question, any known issue of solar thermal collectors and TEGs, thermal electric generators?
This is not my specialty, of course, but I mean, there was also a question whether these are available, and they are available on the market, but as far as I understand, the cost is still a problem compared to PV panels, ordinary PV panels. I don't know if you have something to add, you think?
Yeah, I think I'm quite thinking about this slide. It's still showing the conclusions. I think. Oh, okay.
Oh.
Mm.
Do you need any specific slide?
It's okay. I think that's fine now. So I haven't heard guys clearly about the questions. Can I know the question again?
Any known issue of solar thermal collectors and TEGs?
Oh, okay. I think solar collectors, I think that, as mentioned in my slide, I think it's used to produce the heating. I think thermal energy, which can be used for heating and also can be used in the cooling if absorption chiller is connected. So there are some limitations. I think that this is a stabilization, I think. And because of it's depending on the weather condition, I think sometimes you can't produce, I think, enough thermal energy from the solar collector. And also, it's also the efficiency as well.
Another question on district cooling. Would district cooling increase the overall annual cooling costs for residences when compared to the energy costs of using a mini split, since the district cooling operator has to put a profit margin on the cooling being provided?
Yeah, I think this. I think it depending on the policy. I think the insensitive policy. So the price can be vary at different countries. I think necessarily district cooling is expensive than the traditional air conditioning. This is my understanding.
Another question about the efficiency of district cooling. Why cost of distributing cooling is about 2 times higher than traditional AC because of shifting water source?
Yeah, I think one is it can utilize the the free cooling if the central plant is close to the lake, the seaside, and also it can integrate with the renewables as mentioned. So and also you can utilize some integrate with trigeneration, and also it can work in I think the low ambient temperature time, so that you can produce cooling at low temperature during nighttime, and then you can store the cold energy and then release the cold energy in the daytime. All this can enhance the efficiency of district cooling.
Thank you very much. Back to the heat pumps. How can thermal energy storage like PCM systems contribute to the performance of heat pumps for domestic hot water?
I think there are two things here which could be of importance. One is, of course, that if you substitute a gas heater with a heat pump, you cannot get the same capacity, and thereby it's important to store energy. So if the PCMs can be used to reduce the volume of the water storage, that it would be a good idea. I haven't seen any products realizing this, but we are doing some tests in our lab using combinations of heat pumps and PCM storage just to reduce the storage tank size. And to some extent, this is could be positive. We haven't concluded yet, so there are still some problems with this technology as well. As you know, PCMs are not as ideal, how should I say, as water with a well-defined melting temperature and things like that. So there are problems with it.
Back to the air conditioning. Do you know of an operating seawater air conditioning system that they are operating?
Yes, and there are some examples for the seawater, I think, connect to the central plant. And depending on the temperature of seawater, sometimes it's colder than, I think, 4 to 60 degrees C, particularly in the winter time. So that will be used to directly cool down the return water from the building without using the chiller system to cool it down, to save a lot of energy. So if the seawater temperature is higher for some time, some season, then the I think 6 or degrees C, so it can be used as the pre-cooling strategy to pre-cool the return water. So it can also save energy for the chiller system.
Super. Thank you very much. I think there is another question. In centralized cooling, if HDPE or PVC pipes are used, what is the risk of microplastic, nanoplastic biodegradation over time, let's say 20 to 30 years?
PCT mean the for. So I'm not quite sure about this question. Can you say again, Soki?
For the centralized cooling, that here we're speaking about the piping and the pipes
Yeah.
that's used plastic. So what's about the nanoplastics and microplastic used and the impact over the 2 or 3 decades?
Oh, you mean the nanoparticle mixed
Yes.
with the water supply? I think
Yes.
definitely, I think it can enhance the heat transfer between the distribution pipe flow and water flow, and also the central chiller system. So it can, I think, for example, for the cooling, it can increase the working temperature and enhance the performance of the chiller system. I think that definitely can enhance the performance of the central chiller system.
Thank you very much, professors. Thank you for the Q&A session. Before closing, I just want to inform about the publication coming up on Thursday, the IRNU publication. Keep an eye on the social media, LinkedIn, our website, the new publication called High Temperature Heat Pumps for Industrial Decarbonization, as a second edition of the first publication published in 2022. Thank you for this webinar. Thank you for the 150 plus participants. The recording will be available on our website and shared on our LinkedIn page. Thank you, Professor Palm, Professor Yunting. Thank you very much for your time.
Thank you, everyone.
Thank you.
Thank you.
Thank you, everyone.
Thank you.
Bye-bye.
Bye-bye. Thank you.